Welcome to the tutorial on one dimensional wave equation. In this tutorial we are going to solve a few problems based on the Cauchy problem for the homogeneous one dimensional wave equation. Recall what is a Cauchy problem? Given functions phi and psi, phi is C2, psi is C1 defined on whole of R real line. We need to solve this partial differential equation which is the wave equation ut t equal to c square u x x for x in R and t positive such that it satisfies these two initial conditions u x 0 equal to phi x and ut x 0 equal to psi x holds for every x in R. So, the first problem, show that solutions to Cauchy problem for the homogeneous wave equation have the following properties. What are they? If the Cauchy data consist of even functions, that is the function phi and psi are even functions, then solution also is even function at every time instant, fixed time instant t. Similarly, if the data is consisting of odd functions, solution is also odd for each fixed t. And moreover, if the Cauchy data is also periodic functions, phi and psi are periodic functions of the same period, then solutions are also periodic. So, let us use the D'Alembert formula for solution to the homogeneous wave equation, which is this: u x t equal to phi at these points x minus c t and x plus c t, we take the arithmetic mean and then we take this mean of psi on the interval x minus c t x plus c t 1 by 2 c. Okay. Not exactly mean, it is a t times mean anyway. So, this is the D'Alembert formula. So, phi and psi are even functions, we want to show that u is also an even function. What is the meaning of even functions? Phi of minus x equal to phi x for every x in R. Similarly, psi of minus x equal to psi x for every x in R, even with respect to x equal to 0, that is a correct statement. So, we want to check what u is also even function, that means u of minus x comma t is equal to u of x comma t. This holds. The only starting point is the D'Alembert formula. So, let us write the formula for u of minus x t. It is this. Now, we have to use that the functions phi and psi are even functions and show that this expression indeed equal to u of x t. So, now phi is an even function, therefore, this equal to phi of x plus c t, right, minus of this is this, and here it is phi of x minus c t by 2, okay, because we are using phi is even. This is the first term. Then we have a second term 1 by 2 c integral minus x, I just write as it is from the above. We will handle this separately. I think it is better to work with the two terms separately. So, now let us show that this integral is actually equal to x minus c t to x plus c t of psi s ds. Then what will happen? This is precisely the expression for u x t. That means, we would have shown that the function u is even function. So, we need to deduce this from this is the equality of these two things. Okay. So, that naturally suggests a change of variable to be used, because even in odd functions means some change of variable x going to minus x naturally comes into place. Okay, let us do that. So, what we have is minus x minus c t minus x plus c t, this is the integral that we have. Now, we apply a change of variable, put psi equal to minus tau. psi s ds. Okay. Yeah. So, then what will happen, inside it is psi of minus tau and ds is minus d tau. Okay, fine. And now the limits, when s equal to minus x minus Ct, what will be tau? It will be x plus Ct, because tau is minus s, and when s is equal to minus x plus Ct, tau will be minus s, therefore, this will be x minus Ct. So, now we have a minus sign here, that minus sign corresponds to this change of limits, upper and lower limits. So, I get x minus Ct to x plus Ct d tau minus d tau has given rise to this change of limits, and psi is even. Therefore, psi of minus tau equal to psi of tau. So, therefore, we have shown that u of minus x comma t, we have started with a formula and we have shown it is equal to u of x t. This holds for every x. That means u is an even function. So, let us move on to the next part. If the data is odd functions, phi and psi are odd functions, we want to show that u is odd function. Odd function means what? Odd about 0. Phi of minus x equal to minus phi x, psi of minus x equal to minus psi x holds for every x in R. We want to check that u of minus x t equal to minus u of x t holds for every x in R. The computations are exactly similar to the earlier case. So, let us start computing u of minus x comma t. The D'Alembert formula gives us this, and now we need to use that phi and psi are odd functions. So, therefore, the first thing here is equal to phi of x plus Ct, okay, with a minus sign, and phi of x minus Ct with a minus sign. So, because phi is odd function by 2, and here also we are going to use that psi is an odd function. So, let us compute this integral. Once again use s equal to tau equal to minus s. So, d tau equal to minus ds. Therefore, the integral would become, it is s equal to minus tau, right. So, when s is equal to this, tau will be minus of that will be x plus Ct to x minus Ct. ds is minus d tau as before, and psi of minus tau. But now psi is odd, therefore, in the integral psi of minus tau is minus psi of tau. Now, this minus d tau, the minus here corresponds to change of these limits upper and lower d tau. So, and that is nothing but minus x minus Ct to x plus Ct psi tau d tau. Therefore, what we have obtained is u of minus x comma t is equal to minus phi of x minus Ct plus phi of x plus Ct by 2, okay, that is the first term from here, this term, and the second term is here 1 by 2 c is there with a minus sign, and x minus Ct to this is x plus Ct. Oh sorry, this is for the top one. Yeah, this is x minus Ct, this is x plus Ct sign. Okay. So, this is the first term, and then we have 1 minus 1 by 2 c x minus Ct to x plus Ct psi tau d tau, which is precisely minus u of x comma t. Therefore, if the data is odd, solution is odd at all times. Now let us turn our attention to the last part where the functions are periodic. Say the period is L, which means that phi of x plus L equal to phi x and psi of x plus L equal to psi x. This holds for every x in R. We want to check that u of x plus L comma t is equal to u of x t. So let us start with an expression for u of x plus L comma t. By D'Alembert formula it is this. Now phi is periodic of period L, therefore phi of x plus L minus Ct is actually phi of x plus x minus Ct. Similarly, phi of x plus L plus Ct is nothing but phi of x plus Ct. And if you look at this integral, once again what is this integral? It is actually on what? Which interval? X minus Ct plus L to x plus Ct plus L, this ok. So this under a translation by L will go to x minus Ct comma x plus Ct, this is what we want, right. So this suggests what change of variable we have to put. Let us put tau is equal to s minus L, then what will happen? D tau is ds and this integral will become, when s is equal to x plus L minus Ct, tau will become x minus Ct. When s equal to x plus L plus Ct, tau will become x plus Ct, and integrand psi of s, psi s is tau plus L d tau, but psi is periodic of period L, therefore this is equal to x minus Ct to x plus Ct psi of tau d tau. So therefore what we have shown is that u of x plus L comma t is equal to u of x comma t, that means u is periodic. So what is the importance of this problem? 1, if the Cauchy data is even and periodic, then the solution is also even because Cauchy data is even, solution is also periodic because Cauchy data is periodic. Similarly, when the Cauchy data is odd and periodic, then the solution is odd and periodic. If x going to uxt is even, the function u is even, then dou u by dou x at 0 t is 0. We will show that. And if the function is odd, u of 0 t is 0. So let us prove this. How do we prove that? Let us show dou u by dou x of 0 t, let us compute and show that it is 0. What is it by definition? Limit h goes to 0 u of h comma t minus u of 0 comma 0 by h, okay. And since we know that the function is even, so naturally it suggests that we have to consider h positive and h negative. So we can compute the limits as h coming to h goes to 0 from positive side and negative side. That is what we are going to do now. So limit h goes to 0 from the negative side, let us see what it is. U of h t, this is exactly same difference quotient as before. Now we are going to input this information. So what I do is that I put h prime is equal to minus h, then what will happen? H prime will become positive. So then what I have here, u of minus h dash comma t minus u of 0 0 by minus h dash. Of course, limit h dash goes to 0 from positive side. This, what is this? I have to use that u is even function. So this is nothing but limit h dash goes to 0 from positive side is u of h dash comma t, because u is even with respect to x, minus u 0 0 by minus h dash. Okay, this exists, this limit exists. So what is this? This is actually minus, this minus can come outside, minus limit h dash goes to 0 plus of u of h dash comma t minus u of 0 0 by h dash. This is precisely the right hand derivative at 0 0 with respect to x. This is the left hand derivative, both exist and one is a negative of the other. That implies that dou u by dou x is 0, both of them are 0 and dou u by dou x is 0. So, this shows that if u is an even function of x, then the derivative with respect to x is 0. Now, showing this is much simpler, because u is odd function, right. So, u of minus x comma t, the t does not play any role here, you can think t is not there, equal to x t with a minus sign by odd thing. Okay. Now, let x goes to 0, then the LHS will go to u of 0 comma t, right hand side will go to minus of u comma 0 t. This implies that u of 0 t is 0. So, therefore, if the function is even, derivative is 0 at 0 and the function is odd, then the function itself is 0. Okay, what is the application of this? It will be used in finding solutions to initial boundary value problems. So, let me tell you what is initial boundary value problem. We have discussed this in the last lectures 4.1, we have introduced the initial boundary value problem. So, we want to solve d equal to 1 obviously, and u equal to, let us say, homogeneous wave equation, and here we prescribe u of x 0 to be phi x and ut of x 0 equal to psi x. This is the Cauchy data. So, this let us say 0 and L. So, we are defining let us say u of 0 comma t is given to be 0, this is a boundary condition, and u of L comma t equal to 0, this is a boundary condition. These two are initial conditions. That means, we have a string, finite string 0 L, and we are interested in studying solutions of homogeneous wave equation in this domain, which is 0 L cross 0 infinity. This is where x comma t would belong to, and boundary condition is given as u equal to 0 at x equal to 0 and at x equal to L for all times. Now, in finding this solution, the problem will be useful. So, if you see here, u of 0 t is 0, u of L t is 0. So, one would like to transform this problem to a problem which is posed on full space. So, what one would be interested in solving is this equal to 0 in R cross 0 infinity. But if you want a Cauchy problem in the full space, so you have to give what is u x 0, that I will tell you what it is going to be, some function phi tilde of x. Similarly, u t of x 0 equal to some function psi tilde of x has to be defined for R. So, that means we have to extend the functions phi and psi which are given in the interval 0 L to functions which are defined on whole of R. So, this means we have to extend these functions. How do we extend? So that these boundary conditions are naturally satisfied. So, what is the boundary condition? U of 0 t is 0. That means this function here u of 0 t is 0, therefore, when is u of 0 t is 0? When the function u of x t is odd function. When u of x t is odd function, u of 0 t is 0, we know that. Therefore, what we think is to get u of x t as an odd function, we need the data to be odd function. So, this suggests extend phi and c as odd functions. Okay. So, this problem 1 actually gives us an idea of solving initial boundary value problems. So, extend them as odd function so that solution will be odd, so that u0 t is 0 is satisfied. But how ult will be equal to 0 will be satisfied? That we would like some kind of periodicity. U of 0 t is 0, u of lt is 0 if u is periodic also. Therefore, extend this as odd functions and periodic functions of period L. Then what will happen? Suppose you are successfully have done this, and so that the extended functions have the required smoothness, namely phi tilde is C2, psi tilde is C1. We can solve this problem. Solution in the whole space is going to be both odd function and periodic function of period L, because the Cauchy data is periodic as well as odd functions, and then this naturally satisfies this condition. Boundary conditions are automatically satisfied. If the solution in entire R, of course it will be solution on 0L as well. So, that is the way to solve. So, this is the application of the problem 1. The other part where we have shown that if function is even, dou u by dou x at 0 t is 0 will be applicable for a different initial boundary value problem, where instead of prescribing u equal to 0, we prescribe dou u by dou x at 0 t is 0, dou u by dou x at lt is 0. Then that suggests that we have to extend phi and psi as even functions, so that solution is even and boundary conditions are satisfied. 0 boundary condition is satisfied for dou u by dou x, but I also want at x equal to L, therefore, I will do periodically also. So, in other words, what I am saying is for this problem where u is given to be phi here, I will be brief, it is exactly same as this, ut will be psi here. Here instead of u0 t or ult, what we give is dou u by dou x at lt is 0, and here dou u by dou x at 0 t is 0. In that case, the suggestion is extend phi and psi as even and periodic functions of period L. So, that solution will also be even and periodic, and these conditions are satisfied. Okay, let us move to the next problem. Let u be a classical solution to the wave equation. Show that for each fixed y in R, the new function which is defined by translating u by y is also a solution. Similarly, if u has kth derivative or kth derivative is C2, then you can also take the kth derivative with respect to x and then show that it is also a solution. And this is u of Ax At is also a solution. So, this is a translation of a solution is solution, this is dilation of a solution is solution. Let us do the first problem. So, w of xt is equal to u of x minus y comma t. U satisfies utt minus uxx equal to 0. So, now I have to compute wt and wtt, wx and wxx. Wt is simply ut at the point x minus y comma t. It is better to write the arguments all the time, particularly when there is a chain rule involved. So, wtt of at the point xt is utt at the point x minus y comma t. Similarly, wx of xt is ux, this y does not play any role, it is just translation, x minus y comma t, and wxx at xt is uxx at x minus y comma t. Therefore, wtt minus wxx at any point xt is nothing but utt minus uxx at this point x minus y comma t, and that is equal to 0 because u solves the wave equation at any point x comma t and hence at point x minus y comma t also. So, that means w is a solution to the wave equation. Similarly, you can check the other two parts of this problem. So, equation is translation invariant because the coefficients are constant coefficients, therefore, solution is also translation invariant. A question related to problem 2, the equation utt minus uxx equal to 0 is invariant. This you please check. Under this change of variables xi equal to ax and eta equal to at, the operator transforms to a square into w eta eta minus w xi xi. That means the D'Alembert operator is not invariant under these change of variables. So, the question is what are the linear transformations xi equal to ax plus bt eta equal to cx plus dt under which the D'Alembert operator is invariant. So, that is an exercise. So, let us look at the problem 3. Let u be the solution of the Cauchy problem which is given here, the wave equation here, that means c equal to 3. So, utt minus 9 uxx equal to 0 and initial condition ux0 is this and ut is this, and you are asked to find out the value at the point 0 comma 1 by 6 and discuss the large term behavior of the solution, that is what happens to u of x naught t as t goes to infinity, whether the limit exists, if it exists what is it at every fixed point x0. Now, if you observe the phi x and psi x, phi is discontinuous, right. This is in the interval minus 2 comma 2, the function is 1, outside that it is 0. So, it is a discontinuous function, forget about C2. Similarly, this function exactly functions both phi and psi are same and they are not continuous. So, therefore, we have to exercise caution. The Cauchy data does not satisfy what is required for D'Alembert formula to be applicable. Therefore, the formula does not apply as such because phi and psi do not satisfy the required smoothness assumptions. So, what do we mean by a solution to Cauchy problem as above when the Cauchy data is discontinuous, for example, as here. So, we have not studied such problems, do not give up, do not worry. There are possibilities to interpret the D'Alembert formula as a weak solution. So, when Cauchy data is not smooth as required. Towards the end of our discussion on wave equation, we discussed some notions of weak solutions. So, do not worry, there is some way to interpret this as a solution. So, go ahead and compute. So, such a bad Cauchy data why do we consider? We consider because the computations become easier. As a result, it is easy to illustrate certain features of solutions that we want to show using bad Cauchy data. Of course, good Cauchy data may also be used to illustrate these features, but computations become very difficult, complicated, cumbersome, and our attention will be focused on actually computing solution than exhibiting the features. That is the reason why we use bad Cauchy data, but we should be aware that this is not the Cauchy data for which D'Alembert formula is a classical solution, that we should keep in mind. We have given similar reasons in the context of Burger's equation also in lecture 2.15. Okay, let us solve this problem. Very easy, we have to simply apply the D'Alembert formula. So, first part was to compute u of 0 comma 1 by 6. So, we have to identify what the C is. Our equation is utt minus 9 uxx equal to 0, that means C is equal to 3. because D'Alembert formula is u of x t equal to phi of x minus c t, which is 3 t plus x plus c t. So, it is x plus 3 t by 2 plus 1 by 2 into c, that is 6 x minus 3 t to x plus 3 t psi s ds. Now, it is very easy, u of 0 comma 1 by 6, x is 0. So, phi of 3 times 1 by 6 is minus half. See how simple the computation has become, minus half to half, but on this interval what is psi? It is 1. So, therefore, phi is also 1. So, 1 plus 1 by 2 plus 1 by 6 into this is half plus half, that is 1. So, this is 1 plus 1 by 6, which is 7 by 6. So, this is the answer. Now, let us discuss the large time behavior. So, fix x naught. So, u of x naught comma t, we have the formula above, x naught minus 3 t plus phi of x naught plus 3 t by 2 plus 1 by 6 x naught minus 3 t x naught plus 3 t psi s ds. So, here we have two terms, let us call them a and b, analyze them separately. So, what happens as t goes to infinity? Observe the term a, as t goes to infinity what happens? X naught minus 3 t will go to minus infinity and x naught plus 3 t will become infinity, go to infinity. In particular, after some time x naught minus 3 t and x naught plus 3 t, both of them come out of this interval minus 2 comma 2, because they are going right, because they are going to minus infinity and infinity respectively, they will be out of this interval after some time. We can find out when they will be out. So, that phi will be 0 after some time. Therefore, for t bigger than some number, phi will be 0. So, this term will be 0. For the same reason, this goes to minus infinity, this goes to plus infinity, but psi is defined only on, it is non-zero only on minus 2 comma 2. Therefore, it does not matter what this interval is, after some time it will be minus 2 to 2 psi s ds. So, that is going to be our large time behavior. So, since phi of x equal to 0 for all x which do not belong to minus 2 comma 2, phi of x naught minus 3 t will become 0 for t bigger than x naught plus 2 by 3. In other words, I am just looking at this, I am asking when x naught minus 3 t will become less than minus 2. Similarly, x naught plus 3 t, when will that become greater than 2? And phi of x naught plus 3 t will become 0 for t bigger than 2 minus x naught by 3. So, whenever t is bigger than both of them, phi of x naught minus 3 t as well as phi of x naught plus 3 t will be 0. Therefore, for t bigger than, let us call t star, which is maximum of these two numbers, phi of x naught minus 3 t equal to 0, and that will also be x naught plus 3 t, that will also be 0. In other words, the term a will become 0. Okay. Now, let us look at the term b. For the same reason, the term b, which is an integral on x naught minus 3 t comma x naught plus 3 t, whenever t is bigger than the t star as above, this interval is like this. This interval properly contains minus 2 comma 2. Therefore, this integration x naught minus 3 to x naught plus 3 t of psi s ds is actually minus 2 to 2 psi of s ds. So, therefore, the term B for t bigger than the t star as on the previous slide is actually 1 by 6 minus 2 to 2 psi s ds, which is psi s ds is 1. That is 4 by 6, which is 2 by 3. So, therefore, limit u of x naught comma t, no matter what x naught is, this limit exists and the limit is actually 2 by 3. Okay, let us move to the problem 4 now. So, let phi and psi be C2 and C1 respectively defined on the real line such that phi and psi both are identically equal to 0 outside an interval a b. That is, we have an interval a b. Inside the interval a b they may be 0 at some points, may not be 0 at some points, but definitely outside that phi is 0 and psi is 0. Similarly here phi is 0, psi is 0. And let u be a solution of the Cauchy problem for the homogeneous wave equation. Show that the function x going to uxt, that means you fix a t, then uxt is a function of x, that is also identically equal to 0 outside an interval. In other words, if the data is 0 outside interval a b, solution will also be 0 outside some interval. That interval may not be a b, but some interval. So, the functions f g in this decomposition uxt equal to f of x minus c t plus g of x plus c t. Remember, this is a general solution of the homogeneous wave equation. We derived this in lecture 4.2. So, if the functions f and g are such that they are of compact support, we will define what is a compact support. F and g are compact support, then the integral of psi over r must be 0. Integral of psi over r makes sense and it is 0. Okay, let us start the solution of problem 4. The starting point as before is the D'Alembert formula. Okay. Let us fix a time t equal to t naught. We will show that the function u of x comma t naught is 0 outside some interval. So, as before let us analyze these terms separately, a and b. A is the simpler one to understand. See, a is definitely 0 when under two conditions, any of the two conditions. Our a and b are here, imagine x minus ct is here. Okay, because x minus ct is here, x minus ct will be to the right side, therefore, the term a is 0 because phi is 0 outside the interval a b. So, what is the condition? One condition, x minus ct is bigger than ct naught is bigger than b. That is the case when x is bigger than b plus ct naught. Or the other case is here, x plus ct is less than a. Then also x minus ct is to the left side and phi is 0 on the interval x minus ct, x plus ct, or x plus ct is less than a ct naught. Okay. So, that means that x is less than a minus ct naught. Therefore, if you are on this interval a minus ct naught, b plus ct naught, this is ct naught, the a is 0, a is 0 if x is not in this interval. So, if x lies outside a minus ct naught, b plus ct naught, phi will be 0. Same reason holds for B also, psi will also be 0 if you are outside this interval. So, what about B? The term B, same answer. So, if x lies outside this interval a minus C T naught B plus C T naught, then the terms, both the terms A and B are 0. Therefore, what we can conclude is if x does not belong to A minus C T naught comma B plus C T naught, that implies that u of x t is 0. U of x t may be 0, u of x t naught may be 0 even if x is there inside interval. We are not making any comment on that. What we are saying is u is definitely 0 if x is not in that interval. So, this is what is called data compact support implies solution compact support. Of course, one may want to know what is this support and compact support. Let us define. You can find in any book on topology or real analysis. Let us consider a continuous function from R to R, because that is the situation we are now currently in. Let us consider a continuous function. Then what is the definition of a support of f? This is a notation, support of f. What we have to look at is, look at those points where f is not 0, and take the closure of that. So, by definition support is a closed set by definition, and if it also happens to be a compact set, it is called compact support. Support is always closed by definition. If it also happens to be a compact set, it is called, support is called compact. We know in R compact sets are closed and bounded sets. Therefore, if the support is bounded, then definitely it is compact. Therefore, if the function is 0 outside a bounded set, then the support is always a compact support. For example, let us look at one example, 0 up to 0, 1 after 1 also it is 0, in between it is something like that. In this case, the set where f is not 0 is 0 comma 1, that is a set, and we have to take the closure for the definition. So, that is a closed interval 0 1. If you notice, at the end point 0, the function is 0, but it still comes under the support due to the closure, that is why the endpoints have come in 0 and 1. Now, if you look at another function which is sin x, okay, where it is not 0 is precisely except these points where the sign is 0, which are multiples of pi. So, from R you subtract multiples of pi, integer multiples of pi, right, and take the closure, and that is R. So, the support of the sin x function or cos x function for that matter is R. Support of this function here like this hill is actually the interval 0 1. Of course, there are other characterization of support. This is the definition of support, is look at the points where the function is not 0, take the closure. The other way to look at is that support of f complement is the largest open set on which f is 0. That means, take any open set on which f is 0, keep on collecting such open sets, take the reunion, therefore, you will get the largest open set on which f is 0, take the complement, that will be the support of the function. Verify that this coincides in the previous 2 examples that I have given. Now let us turn our attention to the second part. Second part said u of x t is equal to this and it is given that f and g are functions from R to R, they are compact support. That means they are 0 outside some bounded interval. In other words, f and g are 0 outside some interval which we can take alpha beta. For both of them we can take the same interval, because if f is 0 outside alpha beta, g is 0 outside alpha dash beta dash, by taking the minimum for the left hand points, maximum for the right hand points, we will get common alpha beta. What is important is that f and g are 0 outside the interval alpha beta. Inside what happens, we are not concerned right now. That is given. Then we are asked to show that integral of psi is 0. Okay, let us see what is phi x to start with. Phi x is what? U of x comma 0, that is f of x plus g of x. Of course, outside alpha beta this is 0, right. So, this is 0 outside alpha beta. Similarly, what is psi of x? That is ut of x comma 0, that is nothing but minus c f dash of x plus c g dash of x. If f and g are 0 outside the interval alpha beta, f dash and g dash are also 0. Therefore, this combination is also 0 outside alpha beta. In other words, phi and psi are 0 outside alpha beta. So, we are in the situation of the part 1 of this problem. Phi and psi are 0 outside this interval. Therefore, of course, solution is of compact support for every fixed time, that is fine. Now, what we are interested in is the following. We want to see what happens to the long term, right. Yeah, limit of u of x naught comma t as t goes to infinity. We did this in a previous problem. It turned out that this is going to be 1 by 2 c integral over r of psi s ds. Okay. This is what we saw in that problem. Of course, we computed with the specific numbers and we want to say this is 0. Why? Because what is u of x 0 comma t? You can fix a x 0 comma t. What is u of x 0 comma t? By this expression it is f of x 0 minus c t plus g of x 0 plus c t. Now, as t goes to infinity, x naught minus c t, x naught plus c t will come out of the interval alpha beta. Therefore, that limit is 0. Therefore, we conclude this, that integral of psi over the support must be 0. This completes problem 4. Now, let us move on to problem 5. Let u be a twice continuously differentiable function which solves the wave equation utt minus c square u x x equal to 0. Prove that u is constant and a member of this family x minus c t equal to constant. Just write the picture just for reference, let me write this. So, this is x minus c t equal to 0, these are the lines, okay. These are x minus c t equal to various constants. So, if the solution is constant on any one of them, on this of course it will depend on x and t, right. But if that is not the case, imagine it is constant, then it will be constant on each of those lines. Take any other line, you will be constant. That will be very simple from the representation formula that we have. We know that solution of the wave equation is of this form. We have this formula. Now, as x comma t, this point varies on a line x minus c t equal to alpha naught. So, let us assume that u is constant on x minus c t equal to alpha naught. We are going to show u is constant on any line x minus c t equal to alpha for some other, for any alpha also. So, as x t varies on this line, what happens to x minus c t or x plus c t? X plus c t will vary in R, entire R, but we are assuming u is constant. Let us assume that constant is c alpha 0. So, u equal to c alpha 0 on this line x minus c t equal to alpha naught. Therefore, what we have is c alpha naught is equal to f of alpha naught plus g of x plus c t for all the x t which are on this line. That implies that g of x plus c t is equal to c alpha naught minus f at alpha naught. It means that the function g is a constant function. This implies g is a constant function. Okay. Proof: x minus c t equal to alpha naught, right, that is where the x t is varying. That implies what? C t is equal to x minus alpha naught. That implies g of x plus t c t equal to g of 2x minus alpha naught, and that is equal to this number. What is that number? C alpha naught minus f alpha naught, which is a constant number, it is a constant. So, that is what this implies, that g of any value, g is identically equal to, because as x varies, right, if you consider this line, x is varying, right, throughout. X minus c t is what is fixed as alpha naught. So, x varies to minus infinity to infinity. So, therefore, g is a constant function, g of z equal to c alpha naught minus f alpha naught. So, it is a constant function. So, once it is a constant function, what do we have? U of x t is equal to f of x minus c t plus, let me call beta. So, let us call g is a constant function. So, let us call that beta, a real number. This is what we have. This implies what? If x minus c t is equal to some number alpha, then u of x t is equal to f of alpha plus beta. This, that is, u is constant on each of these lines x minus c t equal to alpha. Therefore, if you have found a line on which u is constant for some alpha naught, u is equal to c alpha naught, what we are showing is on this line u of x t, for x t on this line will be equal to f of alpha plus beta. That means a constant again. Thank you.